Hi everyone! This video is going to take a look at organic isomers, or just isomers in general, really. The word isomer means same units. So iso means same and mer means units. So isomers are molecules that are built from the same units, but they have to be different in some way. And the difference is going to come in their structural formulas. So we're going to take these same units that build this molecule and arrange them in a different way to create an isomer. So in this case, what I've got here is a molecule made of 5 carbons and 12 hydrogens. And you guys know by now that if I wanted to name that, I'm going to take the prefix pent and end it with ane to show that they're connected all by single bonds. And if I wanted to draw an isomer of pentane, what I'm going to do is take that same molecular formula and arrange those 5 carbons and 12 hydrogens in a different way so that I don't build pentane, I build something slightly different. So let's do just that. Let's take the formula C5H12. I know that has to be my molecular formula because otherwise it wouldn't be an isomer. And let's arrange 5 carbons and 12 hydrogens so that I don't get pentane. If I don't want pentane, my number one priority is to not put 5 carbons in a row. Because if I've got 5 linked carbons all in a row, I've got pentane. So if I just try and stick another carbon right up here, that's no different because that still links all 5 continuously. I'm going to have to disrupt that longest chain in some way. And one way to do that would just be to put my 5th carbon right there. So that way, no matter which way I count, the longest carbon chain I see here is only 4 carbons long. So what I'm really doing is taking a 4 carbon hydrocarbon and modifying it with this little addition right here. And one way to check to make sure that you've got yourself an isomer is number 1, make sure that you really did use 5 carbons and 12 hydrogens. But you can also go back and try and name that compound. If you come up with the same name as your original molecule, you don't have an isomer, you have the same thing. So if we go through and try and name this structure that we've just drawn, what I see is, again, my longest chain is 4 carbons, which I usually call butane. But I've modified butane on its 2nd carbon by adding a methyl, or 1 carbon, attachment. So I've ended with 2-methylbutane. I've got a different name, a different structure, and the same molecular formula. That is the definition of isomer and all of the little associated checks you can do to make sure that you've got yourself an isomer and not the same molecule. So we can also look at isomers for molecules that are more complex than just plain old hydrocarbons. So let's take, for example, this molecule right here. It's got a molecular formula of C3H6O2. And I see that this molecule contains this COOH functional group right here. And if you're looking on table R, you'll notice that that's the functional group characteristic of an organic acid. So if I'm trying to name this thing, I'm going to use the naming conventions for organic acids. And that's to take my number of carbons. Oops, not 4, just 3, right? So prop. And I'm going to denote that those 3 carbons are connected by single bonds by using the AN of your alkene ending. And then I'm going to end it with the organic acid characteristic name ending, which is oic acid. So this particular molecule is representative of propanoic acid. I can draw an isomer of propanoic acid by rearranging its molecules in a very unique way, because I can't just sort of toss this carbon right up here or anything like that, because that still keeps it as propanoic acid. What I'm actually going to do is switch around the functional group so that I have a different class of organic molecule to work with and to name. So if I do that, I still only have C3H6O2 to work with because I need to build an isomer. But if I want to rearrange the structure, what I'm going to do is take a functional group that's very similar to the organic acid functional group, but move it into the middle of the molecule. So it becomes one of those functional groups that divides up your hydrocarbon chain, and that's the functional group of the ester. So if I take that functional group and knock off the H and instead divide up my carbon chain, looking at this, I've still got 1, 2, 3 carbons, 2 oxygens, and if I fill in my hydrogens, 1, 2, 3, 4, 5, 6, I still have 6 hydrogens as well. So you can go from one class of molecule to a totally different class of molecule and still be considered an isomer because you've used the same molecular formula and altered the structural formula. And again, even though this one is fairly obvious that we have a completely different molecule because our atoms have shifted so drastically, you can go through and name it to make sure that you don't still have propanoic acid. And again, this functional group right here is characteristic of an ester. So I'm going to use the ester naming conventions, which are the more complex ones. So check out that video if you want some extra help figuring the naming conventions for esters out. But I see on this right-hand side, so right of the O, I see methyl attached to my 2 carbon chain that is attached to my double bond. So that's going to be the second part of my name. So I'm going to do eth for 2 carbons and for single bonds over on this main chain. And then I'm going to end it with the O8 ending characteristic of esters. So in this case, I definitely do have 2 completely different molecules that fall into 2 completely different classes of organic compound. But because they have the same molecular formula and different structural formulas, I know that they are isomers.